Hello everyone, today we will undertake the third class of Python Web, which will still cover Python basics, but we will also touch on relatively advanced topics, including error types and exception handling. In the process of Python programming, how do we deal with character encoding and other encoding problems? In the third part, we introduce how to write a function in Python. In the fourth part, we will talk about the concept of variable scope in the Python programming language. Let us first look at the types of errors in our programming process and how we deal with these exceptions. There are three main types of errors: compilation errors, runtime errors, and logic errors. Let's take a look at the meaning of these three types of errors. The first is a compilation error, also known as a syntax error, which is an error generated when the code is compiled. It is usually caused by the code of the program not conforming to the rules of a certain programming language. For example, we may have misused Python keywords, or when writing a Python module, the statements were not aligned within the code block. With runtime error, there is no syntax error in the Python program we wrote, but the error occurs during runtime often when an operation cannot be performed. Runtime or real-time errors only occur when code is running and are thus relatively more difficult to troubleshoot than compilation errors. For example, if we perform a division operation and the denominator is 0, a division by zero error will occur. There may also be out-of-bounds errors, missing methods, attribute errors, and so on. Now let's take a look at what is a logical error. Logical errors occur when the actual result obtained by the program is inconsistent with the accepted result. Usually, logic errors are caused by blunders in the algorithm design or logic design during the code writing process. Compared with runtime errors and compilation errors, logic errors are more difficult to troubleshoot because the code will not report errors during the execution process, but the output results are incorrect. But sometimes our verification of the output results may not be very detailed. Therefore, these types of errors become more difficult to spot. For example, say we write an addition operation, call this method to execute 100 plus 10. Our expected result should be 110, but the actual output returned is 10, obviously not meeting our expected result. At this time, a logic error occurred. One more thing regarding why logic errors are more difficult to troubleshoot. If we write a complex system, every component may contain logic errors. When sequenced together, the complex system then generates an overall error. At this time, we would need to troubleshoot which process caused the error, which often becomes a strenuous exercise. Now let's take a look at an exception handling specifically and first introduce why there is such a design. Why don't we simply use if-else to print out the error message? Let's take a look at why exception handling is a better alternative. The first reason is that if we do not deal with the exception, the program will terminate during execution because an error occurred during its operation. This is not a desirable result. Secondly, say we call a specific third-party library. Previously, we introduced the fact that Python has a wealth of third-party libraries. Therefore, we often cannot pinpoint exactly where an exception may occur, which means we can't use if-else to touch the exception. Take a look at the figure on the right. It represents the hierarchical structure of Python exception classes. First of all, it has a base class, which is a basic exception class like base exception. On top of it, 4 types of exceptions are defined, including exception, system exit, keyboard interrupt, etc. In practice, what we commonly use are exceptions in the first class, which is further divided into 3 categories, one of which is a standard error. What is included? It includes memory overflow errors, runtime errors, syntax errors, etc., structured as illustrated. Now that we've established a basic understanding, let's take a look at what are some of the common syntax errors or compilation errors. These types of errors are usually due to carelessness in the programming process, such as not having matching delimiters, lacking indentation, or keyword spelling errors. On this slide, I have listed several specific examples. Let's look at the first one. We define a string called "I like eating apple" and assign the string to the variable stir. We can see code should be wrapped in double quotation marks or single quotation marks. However, due to carelessness, the ending double quotation mark is missing. When we run the program, it will report a syntax error, stating that an ending delimiter is missing. Let's look at the second example. We want to print the string "Hello Python." The string passed to the print function also needs to be wrapped in double quotes, but we are missing one. It returns the same missing delimiter error. In the next example, we have defined a function. Inside the body of there are 2 lines of code. A line of code performs an addition operation and assigns the result to a variable. The second statement is to return the result of the addition. Within the same function, it needs to have a line indentation, which we talk about in more detail later. We can also see that the indentation is not aligned, so it will also generate alignment syntax errors. In the next example, we assign a value of 100 to a variable, and we want to print the value of this variable. We use the Python keyword print. However, we failed to spell the keyword completely in the code, which is also a typical syntax error. Now let's look at runtime errors. Runtime errors are also known as exceptions. This type of error is the most commonly occurring and the one that needs to be dealt with the most. With syntax errors, we can avoid them as long as we are careful, but runtime errors are the most common. So, what are the main runtime errors or exceptions? For example, if we call a function before defining it, it will cause runtime exceptions. Also, specific to certain Python data structures, such as lists, tuples, etc., which we talked about before, if we extract a specific element in the data structure, the common runtime error is an index out of bounds error. This will also occur if we call methods or attributes that do not belong to an object, or when we try to extract a dictionary value using a non-existing key. We talked about this before. We can extract a corresponding dictionary value using its key, but if we pass a non-existing key, it will generate a runtime error. Then there is attempting to convert a value to an inappropriate data type, attempting to concatenate strings with numeric values, opening a file that does not exist, and so on. These are common runtime errors. We also call it an exception. Look at the example on the right. We have defined a function, or you can also see a method. The purpose of the function is to open a file, and the parameter passed in is the path of the file. When we call such a method, if the path we passed in does not exist, will it report a runtime error? It is reporting a specific error, that is, the file not found error. Let's continue to look at the other 8 main runtime errors. One is the division by zero error. That is, in the division or modulo operation, if the divisor is 0 or the modulus is 0, this error occurs. Let's look at the figure on the right. In this same code, we assign a value of 10 to A and a value of 0 to the variable B and try to run C equals A divided by B. At this time, the divisor B has a value of 0, so the code will generate a division by 0 error. Further down, there is an example of name error, which means a Python object is not declared or initialized before being called. That is, when we try to use an undeclared function or variable, this error will occur. In the example on the right, we assign 10 to the variable A and perform a division operation dividing A by C and assigning the value to D. But we know that C is not defined, so a name error will be reported. The third error is the key error, which is caused when we try to extract a value in a dictionary using a non-existing key. Let's look at the example on the right. We have defined a Python dictionary data structure. There are two sets of values in it. The key and value of the first set are Tom and 18 respectively. The second set is Jock and 20. However, if we want to use the key Abby to extract a value, we know that such a key does not exist in the defined data dictionary, and a key error will be reported at this time. Okay, let's look at the fourth one. The fourth type of common error is type error. Certain functions or methods are only applicable to specific data types. If the data type is not handled properly, this type of error will occur or result in an invalid operation on the type. Let's take a look at the example on the right. We assign an integer value of 100 to a variable salary. We want to increase the value by 20. But by mistake, we use 20 as a string type. Then we know that when we try to add an integer type to a string type, this error will occur. The fifth is a value error. When the input type is correct, but the specific input value is wrong, it will generate a value error. The example on the right illustrates this point well. If we take an integer type, we can convert it into a floating point type using the float function. When we print out the floating point number, it becomes 10.0. But if we try to convert a string using the same function, it will generate a numerical error, because we cannot convert a string like Tom into a floating point value. So the data type we passed in is not incorrect. That is, the string type, but the value represented by the string is inappropriate. Therefore, you must be extra careful during the programming process. The sixth type of error is an index error, meaning we try to use an index that is out of bounds, or if there is no such index in the data structure. Let's look at a specific example. We define a list. There are 6 values in the list, numbers 1 through 6. In the previous lesson, we learned that we obtain a specific value in a list using its corresponding index. For example, print list 1, 0. The value of the 0th index should be 1. Don't forget that the index of this data structure in Python starts from 0. If we want to get the value corresponding to the index position 6, will it cause an error? It will, because although the list has 6 elements, its index only runs 0, 1 to 5. Index 6 does not exist. Therefore, at this time, an index out of bounds error will be reported. But now let's look at the case of extracting a sublist of a list. We see that it is possible to cross the boundary, because we know the expression list 1, 3 to 6 means I want to get corresponding values from positions 3, 4, and 5. The value returned is 4, 5, 6. When a sublist is extracted this way, if it finds that the index at the end out of bounds, it will not attempt to extract it. It will extract the elements from the starting index to the end of the list index. Another type of error, the 7th type, is attribute error. This occurs when we try to apply an inappropriate function or method to an object, or reference an attribute of the object that does not exist. In the example on the lower right corner, we know that tuple in Python is an unmodifiable data structure, so it is impossible for us to add new elements to a tuple like with a list. Therefore, it will report that the append method or attribute does not exist at this point. The eighth category is the memory overflow error. This mainly refers to the excessive memory being occupied during the running of the program, causing the inability to reclaim memory by the system, which in turn causes the memory required for the running of the program to exceed the maximum memory that the system can provide. At this time, the program can no longer run. A typical example is that we are using Python to load a large file, but the operating system running Python cannot provide the necessary memory, which makes the large file unable to load. A memory overflow error will occur in the Python program at this time. Let's take a look again, since there could be numerous exceptions occurring during the running of a program. How do we handle the exceptions? In other words, why do we need to handle exceptions? We know that it may be relatively simple to spot syntax errors. If we adopt an integrated development environment, the IDE itself will take the initiative to help you check Python syntax errors. If you have a syntax error in the process of writing Python code, the IDE software will directly report this error. So, it is easy to troubleshoot. In the development environment, the color of each word of the code will be different. Let's talk about the meaning of the different colors. For example, brown represents a keyword in Python, light yellow represents the definition of a function, light green represents a string, etc. Okay, let's take a look at how we deal with runtime errors. When a program encounters an exception, it is often directly interrupted and execution is terminated. However, sometimes we need to perform additional processing when encountering an exception instead of directly letting the program terminate. At this time, some manner of exception capture is needed, such as try except else, and so on. Through these statement blocks, we catch some of these exceptions, and after the capture, we can deal with the exceptions. Let's take a look at it in detail. Let's first look at the try except statement. This is the most commonly used code block for catching and handling exceptions. The structure of its specific code is like this. First of all, there is the try block, which will execute some code. If an error occurs, the except block will handle the exception. Let's take a look at the code block inside the try keyword. It executes the code normally. If a portion of the code contains an error, it will skip the subsequent code and go directly to the except code block and execute this part of the code. This part of the code mainly functions to deal with exceptions, and we will look at some specific examples later. Let's now introduce the try except else statement. We see that the else code block is added after the try except code block. What is its function? If no exception occurs during the try execution, it will skip the except code block and enter the else code block for execution. However, if there is an error in the execution of the try code block, it will enter the except code block and no longer execute the else code. Now let's talk about the finally keyword. We can directly add the finally code block after either the try except or try except else statements. It means that whether or not a runtime error occurs during the execution of the try code block, the code inside the finally code block will be executed. Its specific execution process can be expressed with the figure in the lower right corner. First of all, we need to run the contents of the try code block. If an exception has occurred, we need to detect an exception has been reported. If an exception is reported, we will execute the except code block. If one is not reported, we will execute the else code block. But in the end, regardless of whether an exception occurs, we will run the finally code block. That's the overall processing logic. Thus, by using modules such as try-except, although we can catch all the exceptions that can occur, we are not distinguishing what the exceptions actually are. This is not a great approach. If we don't identify the specific abnormality in the program, it makes it more difficult to debug. However, we can pinpoint the specific exception that needs to be caught in the except code block. In the example on the right, the try block executes several lines of code that we use except to catch possible exceptions in the try code block. What is the specific exception we want to catch? It is I/O error. Only when the exception that occurs in the try code block is an I/O error will it be caught in the except code block. In this manner, if a division by zero exception occurs in the try code block, will the except code block catch and handle the exception? It actually won't, because it is designed to only catch I/O error. By writing the code in this manner, the programmer can control what exceptions may occur in the try code block and deal with them accordingly. If an error occurs during program execution, it becomes much easier for us to locate the specific abnormality. Let's look at exception handling again. It has some simple methods. There are mainly three special simple methods: assert, with, and raise. The assert statement is to use determine whether or not a specific condition is met. If such a condition is met, it will not throw an exception. If it is not met, it will actively throw an exception. The structure of the code is the assert keyword, followed by a Boolean expression, and finally, a parameter is passed in. The parameter is a specific piece of information that can be returned when an error occurs. But this can be skipped in favor of just reporting the exception without running any specific information. When the Boolean expression is true, the program will skip the assert statement and continue execution. But when the Boolean expression is false, an assertion error will be thrown, and the subsequent parameter will be returned. Why do we need an exception handling method like assert? This is because in large-scale coding projects, we often use assert statements as defensive programming. Before a specific exception is thrown, it is evaluated first. Let's take a look at a specific example below. A simple function is defined. The function passes in a parameter s. It tries to convert s to an int type and assign the value to n. If n is not equal to 0, the Boolean condition is true. We then execute the next line returning the result of 10 out of n. Because n is not equal to 0, and will be no division by 0 error. But if the value of s we pass in is 0, then the Boolean condition is false. At this time, it will actively throw an assertion error. And the error message returned is n is 0. Let's take a look at the specific call. The parameter we pass in for the foo function is 5, which is not equal to 0, and it will execute normally. It returns the result of dividing 10 by 5, which is 2.0. But if we call the foo function and the parameter is 0, we see that it will report an assertion error at the end. The specific information of the exception is n is 0. At this time, programmers can easily spot that a division by 0 error has occurred. We've made an evaluation in advance so that the program doesn't need to terminate. Let's look at the with statement. What is its main function? Sometimes a programmer opens a file, and after he finishes reading the contents of the file, as we said before, we need to close the file handle. But if we forget this piece of code, the file handle will be continuously occupied, which causes errors if other processes try to read the file or operate on the file. When we try to open a file, the file may not exist, or an error occurred when reading the file. We can then use the with statement to easily resolve such issues with reading or writing to a file. Let's look at a specific example. It is written as such: with open a specific file, and the file handle object of the open file is assigned to F. We can read the contents of the file through the F object. These 2 lines of the code are equivalent to the following 3 lines of code. First, we open a file through the default built-in Python method, open. After reading, close the file handle. The F close line is the easiest thing for programmers to forget, but using the with statement is equivalent to automatically adding the F close statements to the compilation process. So it doesn't matter if the programmer forgets to close the file handle. In addition to with, we can also actively trigger exceptions. Using the raise statement, we don't throw an exception during program execution, but rather proactively throws it without handling it. This is similar to the throw keyword in the Java programming language. We've caught the exception in the current code block, but we choose not to handle it and directly throw it to the upper layer of the calling code for processing. This is done with raise. I specify an exception that I want to throw and what the specific exception is. I can also pass in some parameters and whether or not to track the call stack that throws the exception. In such a syntactical structure, exception is a parameter or the exception type. It could be any of the standard exceptions in Python, such as key error, name error, etc. Aux is the parameter the code block itself provides. Usually, just like with the assert statement, it is a description of the exception. The last parameter is less practical, and its main function is to track the abnormal object. Let's now look at an example of a specific code. We first define a method of our own. The name of the method is myException. The processing logic executed here is also very simple. The parameter passed in is called level. If the value of level is less than 1, we will throw an exception. The description of the exception is, it is an illegal level. Let's see how we use this method of actively throwing exceptions. We called the function in the try code block, and the value passed in was 0. In the accept code block, we catch the specific exception and print out the error information. Else specifies if there is no error, print 2. As we said before, if there is no error in the try code block, it will enter the else block. Looking at this code, what should its output look like? First, the value passed by the my method is 0. We know that inside the method, it will evaluate level and throw an exception if it is less than 1. 0 is less than 1, which means it will throw a standard exception and return the description of the exception. At this time, an exception has occurred. It will be caught by the accept code block as designed. We've not handled the exception other than printing the value, which is 1. What follows is a description of the exception. So the printed result should be 1 space invalid level. We can see how raise actively throws exceptions and try except and else catches them. Another situation is that users can define exceptions themselves. Why do users use to define an exception? Because the built-in exception types provided by Python cannot meet their specific needs. When the programmer predicts the occurrence of a certain error, he or she can customize an exception class. In this process, we must first inherit a standard Python exception class and makes an extension based on it. For example, in the list below, we've defined the mySelfError exception class. It is an exception class inherited from exception Python. We have not written the process to handle the exception. How do we call it? We pass myself error to raise. This is the type of exception we have defined, and its error message is a parameter that contains a description. We can now use this class. Let's look at a specific example below. First of all, the user defines a not-stir error, which means that the user specifies the value passed in must be a string type. If it is not, we will report a not-stir error. An initialization method is defined as such to assign the error information. Let's take a look at how to call this method. We've defined a list with several elements in this list. Some of these elements are of type int and some are of type string. Now we traverse the elements in list using its indices. We evaluate whether the element at each index position of list A is a string. If it is not a string type, the user-defined error not-stir error is actively thrown, and a description of not a string element is given. We use the except code block to catch such an exception. Regardless of whether an exception occurs, we will print out the value of each element, which is the operation performed by the finally statement. For this specific example, the result of its output should be like this. First of all, for the element 1, if it is not a string, it will enter the except code block. The information it prints is a description of the exception, not a string element. However, regardless of whether an exception occurs, it will enter the finally module and print out the value 1. So it is 1. For the element 3, it is also not a string type, and the description of the error and its value are printed. For the third element, it is a string, but it is a noun value, so it will not print the exception description, but its value will be printed, which is actually a noun value. So it looks like a blank line. For the fourth element A, it is also a string type, so it will not throw a user-defined exception, but will print the value A. So this is the final result. Now that we've learned about Python error types and exception handling methods, let's look at a string encoding. Why do we need string encoding? This is because what computers store are not the characters recognized by humans, such as ABC 123, or characters in Chinese and Japanese, but rather binary values. Python and other programming languages usually only recognize one type of encoding, so it needs to convert between different types of encodings, making the mapping of encoding types necessary. First, let's look at what is encoding. That is, we map human characters to the binary code a computer can recognize. What is decoding? Decoding is the opposite process. It is when we decode binary code into real human characters. The interpreter in the Python programming language does not recognize the Unicode encoding, but instead receives the string type encoding. Therefore, even if the input data is Unicode encoding, Python will automatically convert it to string type encoding. We will talk about the specific encoding types later, but we must first know that there is such a process. Let's take a look at the specific process of encoding and decoding. A string of string type is converted to a Unicode format through the decoding function decode, and Unicode code is converted to a string type through the encoding function encode. Let's take a look at the specific code execution. Say we assign the string Tom to the variable x, and we look at what type it is exactly. We can print out the type of x by using print type x. We see that its type is string. Now we can make it a Unicode type by decoding it using x, decode, and assign it to the variable y after decoding. We proceed to print the type of y and find that it's Unicode. The reverse process is that we add a character u in front of a string, which means that the encoding type of the string is Unicode. If we now print the x type, it is Unicode. If we encode Unicode variables, it just returns the stir type. The 2 points we need to pay attention to are that in the Python 2.x branch, there are 2 encoding types for strings. One is stir and the other is Unicode. But in Python 3, the corresponding encoding types are stir and bytecode. In the follow-up, we will also see the specific differences between Python 2 and 3. Let's talk about the concept of character sets and the main types. When the computer was first designed, We knew that it only recognized zeros and ones, that is, it used a binary to represent all data. In the beginning, the computer designer thought of assigning a unique string of 0 to 1 for each character. For example, in the ASCII code set, for the uppercase character A, its binary code is 0, 1, 5 zeros, and 1. In addition to ASCII encoding, there are other character sets in computer systems. For example, Unicode, UTF-8, UTF-6, GBK, etc. Let's briefly introduce these character encodings. Let's first look at the ASCII encoding, which uses an encoding system represented by 8 bits. How many characters can 8 bits represent? It is the 8th power of 2, that is, the ASCII encoder can store 256 such human characters. It is the standard established in 1967. At that time, it mainly considered users in the English world, so 256 characters were enough. But for Chinese, Japanese, Korean, etc., it cannot cover the character set of these other languages. The figure on the right is a mapping table. Just now we saw the capital letter A, which corresponds to an 8-bit binary string of 01000001. For example, the ASCII code for the value 0 is 0011, 4 zeros. In this way, human characters, including punctuation marks, can be represented as an 8-bit binary string. This is ASCII. Now let's look at the GBK character set. This was established by the Chinese State Administration of Standards in 1980. It mainly contains 6,763 commonly used Chinese characters and 682 non-Chinese characters. Through the GBK code, we can essentially express all of the common Chinese characters and some non-Chinese characters. Let's look at the Unicode encoding. Its encoding method is the same as the above-mentioned ASCII code, and GBK mapping a character to a specific binary code. On the right is such a mapping table. We will not cover this in further detail. Let's see how the string type encoding is represented in Python. In Python 2, there are 2 data formats for character processing, str and Unicode. The str type is a byte stream. It is assigned with 2 single quotes or 2 double quotes. Accessing an element is actually a byte. For example, for a Chinese character string like Hanyu on the right, we use a single quotation marks to assign its value to the variable x and print x. It is the encoding type seen here. If we use Unicode to represent the Chinese character string, just add the character U in front of it. Printing it out results in this encoding structure, because we know that Unicode uses a hexadecimal code. Therefore, it corresponds to 2 encoding values in Unicode. Let's look at Python 3. In Python 3, the data format used for character processing is str and byte. The str class contains Unicode characters. No issues there. For non-Unicode encodings, such as UTF-8 and GBK, they are defined as byte, which can be converted back and forth through the encode and decode functions. The figure on the right shows this conversion method. We see that the Python string is assigned to the variable x. We print out its type and its str type. We can encode it into a specific UTF-8 format. If it is encoded in UTF-8 format, as we print its type in Python 3, it is expressed as the byte type. After decoding, it is again typed as str. Let's take a look at the situations for garbled characters, special characters, or Japanese, Korean, Chinese, and so on. If garbled characters occur, how do we troubleshoot it? Generally, this situation is likely to be caused by transcoding. The main points of the investigation are as follows. First of all, let's take a look at the Python interpreter and what the default encoding is set at. Then for the program itself, what is the encoding set at in its source file? That is to say, whether you print or display on the terminal, what is its encoding setting?
Usually we need to have these three encodings matched to avoid garbled characters, which is the encoding of the Python interpreter. It refers to the default character encoding method in Python, which is stir type. For a specific stir variable, when converting it to Unicode, the default conversion method for the Python interpreter is ASCII code. We can see the default encoding of the Python interpreter through the getDefaultEncoding function, which shows the encoding in the current Python environment. The source file encoding refers to the Python code source file encoding. When writing Python source files, you can also specify the encoding. The method used is to add a line of coding instructions to the header of the original file. For example, we can use UTF-8 format or GBK format. This expresses the encoding format of the Python source file. The third is the display terminal, which also has its own encoding system. If the string encoding system output by Python is not compatible with the encoding system of the display terminal, garbled characters will occur. For example, the terminal for the Chinese version of Windows uses the CP936 encoding system by default, which is usually regarded as GBK encoding. In Linux, the terminal uses UTF-8 encoding by default. Therefore, if we use the Chinese version of Windows to write a Python program and copy the program to a system terminal such as Linux for display, garbled characters will appear at this time. By making sure that the encoding matches in the three environments above, the issues of garbled characters can usually be resolved. If you find that this is not the case, then the encoding system of the text you are dealing with may be relatively special. At this time, we can use a third-party package of Python called Cadet. Its main function is to test what the encoding system of the text is and return a confidence level. We can install such a package in the Python runtime environment through pip install. Let's look at a specific example. After we install this detection tool, we import it into the current environment. We assign a very long string to the variable string. We print out its possible encoding result through the cadet detect string variable, which returns a dictionary. There are two elements in the dictionary. The first element is its confidence level, and the second element is the type of encoding. That is, how likely is it of the encoding system detected? If the confidence level is 1, it is 100% sure of the underlying encoding system. If the value is relatively small, it means that it is not sure of the exact encoding. Above, we introduced the main encoding systems in Python and the differences between Python 2 and Python 3 encoding. Next, we will talk about how to write Python functions. First, let's take a look at what a function is and introduce the concept of a function. The concept of functions not only appears in Python but also in other programming languages, such as Java as well. Functions strictly adhere to syntactical standards. Its main advantage is that it can be reused. When a function is defined, it can be called multiple times to realize the reusability of single or related code blocks. We know that in Python, there are many built-in functions, such as print. Programmers can also create their own functions, which are called user-defined functions. Programmers can define a function for a specific purpose. Here are some rules on how to define a function. In Python, code blocks usually start with the def keyword. It is the first three letters of define followed by the name of the function and a round parenthesis. Inside the parentheses are some parameters being passed into the function. Let's look at the format of specific function definitions later. Now we first define an addition function, which implements the addition of two integers and returns the result. It is a function like the following. Let's take a look at the upper right corner. This figure represents the structure of the function. First of all, def, which is a keyword of Python, addition is the name of the function, and the parameters passed in the parentheses are the function parameters, which are indented. The 4 lines indented inside represent the body of the function and is the code being executed. The first line is to determine whether the x parameter is an integer type. The second line is to determine whether the y parameter is an integer type. The third line is to add x and y and assign it to a variable z. The fourth line returns the value of z. This is how we define a function for adding two integers. Let's see how to call this function in detail. If we assign both x and y a value of 2 and we call the addition function passing in x and y as parameters, we then assign the result to both x and y. When we print addition x, y at this point, shouldn't the value of x, y become 4? If we perform the addition again, the result will be 8. This is our final output. Now let's talk about the ways to pass in function parameters. There are 4 main ways: positional parameters, keyword parameters, default parameters, and variable length parameters. We define a polynomial function with 3 input parameters x, y, z, perform a polynomial operation and return the result to a variable. When x, y, z is equal to 1, 2, 3, we can call such a function by passing in x, y, z in position and return the calculation result. This is the standard way of passing parameters. The second is to use keywords. That is, the function is the same, but when we call it, we pass in the parameters by assigning keywords to the parameter. If x, y, z is still equal to 1, 2, 3, the return value should still be 11. We can also mix the positional and keyword methods. For example, for the first parameter, we use the positional method, and the value 1 is passed in. For the second and third parameters, we pass in by ways of keywords. This is also possible. But if the first parameter we pass in is in the form of keywords, the subsequent parameter input must also be in the form of keywords. If not, an error will be generated. In the following example, the first position x equals to 1 is passed in as a keyword. The second 1 equals to 2 is also passed in as a keyword, but the third value is passed in by position. If we call the function in this manner, it will cause an error. The third way is to set default parameters. Now our definition of the function changes a bit. Both x and y are parameters without default values, but we can make the default value of z equal to 3 when the function is called. For our third position z, we can choose not to pass it a value. In this case, it will use the default value when the function is defined for calculation. Let's look at variable length parameters again. There will be a scenario when you want a function to accept and process more parameters than when it was originally declared and defined. Then you can use variable length parameters. That is, the redundancy of the function parameters is realized. When the actual number of parameters passed is more than the formal parameters of the function, an error will generally be reported. But with variable length parameters, the function can absorb extra parameters. That is to say, the above-mentioned problem can be resolved by using variable length parameters. Let's look at the function definition. The function is to print the Fibonacci sequence. The first parameter is x, which is an ordinary parameter, and the second parameter is a variable length parameter, indicated by a preceding asterisk. When we call the function at this time, the parameters we pass in can be 1, 2, or even more. For example, when calling the function below, we pass in 4 parameters, 1, 1, 2, 3, and the result it returns is 2, 3, 4. Within the function body, we've traversed the variable length parameter. After the traversal, the summation is performed because the value of x is 1. The ensuing 1, 2, 3 belong to the variable length parameter. It is actually creating a tuple. We traverse each element into the tuple and add it to x. That is, add x with a value of 1 to each of the ensuing parameters 1, 2, 3. So it should print 2, 3, 4. Of course, we can pass it more parameters without any issues. Variable length parameters can also be passed in as a list. For example, we define a list of parameters as 1, 2, 3 and pass in the list. It gets parsed into 3 separate parameters for operation. If you pass in multiple lists in the variable length parameter, They will be packaged into a Python tuple for operation. For example, now we have defined a function. The first parameter passed in is name, the second is age, and the third is a variable length parameter. These three parameters are directly printed out in the function body. When we call the function, you can see that our first parameter passed in is Tom, the second parameter 18, as well as the third and fourth parameter, which are variable length parameters. These two lists will be directly packaged into a tuple in Python and printed. When we use variable length parameters, we need to pay attention to the fact that if we pass in several variable length parameters and the calling function tries to use keywords to pass in the parameters, an error will occur. That is to say, mixing the use of keyword parameters and variable length parameters is not supported. We can only utilize positional parameters in this case. As we just mentioned, variable length and keyword parameters cannot be mixed. However, we can resolve this by adding two asterisks in front of the variable length parameter. In this way, you can use a combination of keyword and variable length parameters. Let's look at the first parameter of our call. The name is Tom, and the second parameter, we've used a keyword. The keyword is that age is equal to 18, and parameters are passed to the function. The third and fourth parameters also use keywords, but are also variable length parameters. When the variable length parameter has two asterisks in front of it, it can mix used in this way. If we now print each parameter, we will run not into any issues and no runtime error will occur. Now let's talk about lambda functions. This is a special function of Python, and it is also a function unique to Python. Lambda itself is a keyword reserved by Python, and it is a simplified way of function definition. What are its characteristics? Lambda functions are anonymous functions. The so-called anonymous function, in layman's terms, is a function without a name. Lambda also has input and output because functions always have to input some parameters, return or output some results. The input is the value of the parameter list passed in, and the result is usually the result of the expression calculation. Lambda function has another characteristic, which is that they are usually relatively simple. Because it is a one-line function, the functionality will not be too complicated, and since their purpose is straightforward, there's no need to explicitly give them a name. Let's take a look at the lambda function we defined for adding three values, which is very concise. We start with the lambda keyword. The three parameters x, y, z are passed in. The body is actually x plus y plus z. This line of code constitutes a lambda function. The lambda function can be assigned to a function variable, which is multisum. When we call the lambda function, we call it through the variable multisum, which is a kind of function variable. We can call the lambda function by passing in three values to it, which is 1, 2, 3 to sum. It returns the value of the sum, which should be 6. Lambda function is a concise way of achieving this. When the user is writing some code with very simple functions, we can utilize lambda functions, which improves efficiency. We have now introduced some basic knowledge of function writing in Python. Let's talk about the concept of variable scope in the Python programming language. The scope of variables in Python is made up of two types, local variables and global variables. Let's take a look at why this is. This is because they are used in different scenarios. Local variables are used when they only need to be visible inside a function and not outside. That's the usage scenario of local variable. What are its advantages? Because it is locally visible, it becomes safer. It's less likely to cause some uncontrollable issue if the programmer makes a syntactical error. The disadvantage is that it can only be seen locally and not visible outside the function. So if you tend to only use this variable inside a function, a local variable should be used. For global variables, its main usage scenario is if a variable needs to be used by multiple different functions. There are some typical situations. For example, when we define a class, the member variables are usually global variables. Say, we define a student class which contains name, age, class, selected courses, and grades, etc., These variables are the member variables of the class and are usually defined as global variables because they may be used in several methods inside the class. What are the advantages of global variables? Because they are visible within the entire Python module. They can be used by different functions. What are their disadvantages? Precisely because they can be used by different functions, each can modify this variable, which makes the program more prone to errors. Therefore, deciding whether to use local variables or global variables depends on your specific usage scenario. Here we can apply a well-known theory in the computer science field called Occam's razor theory. The basic idea is that we should adopt an appropriate methodology for any given scenario. Let's take a look at the difference in the use of local variables and global variables. Once again, local variables refer to those that have a fixed variable scope, and only those variables that can be called within this scope are local variables. For example, now we have defined a method called selectMax, passing in a parameter x, and the code body is as such. First, we import the Python system library sys. Within this module, we will get the maximum value of the Python can express. Of course, we added a negative sign -1 to express the minimum value. If x is a Python list, we traverse each element in the list, hoping to find the element with the largest value, executing the following logic, and we finally return the maximum value. In the code body, the variables sys, max value, and I are all local variables. We call the function passing in a list of 1, 2, 5, 1, 1, 1. The maximum value of the list should be 11. After executing the code, we will get the value of the largest element in a list. We know that local variables can only be used within the local scope. Beyond it will result in errors. We mentioned that max value is a local variable within the selectMax method. If we want to print its value or use it outside of the function, it will cause an error. The print statement here, through its indentation, we can see that it does not belong to the body of the selectMax method. If we try to print the value like this, it will report an error. The max value variable is simply not defined outside the function body and therefore not visible. For the variable x, let's take a look. It is defined outside of the function, so it should be a global variable. But then it cannot be modified inside the function body. So when we call this method, it will say that the local variable x has not been allocated before being referenced. Before such a variable is not defined inside the function body. We will see the difference on the next slide. Let's look at global variables again. They are global relative to local variables. The scope is global. That is, after the initial definition and assignment, global variables can be referenced in all functions, classes, and lambda functions. The variables defined outside the keywords def, class, and lambda are all regarded as global variables. Earlier, we have defined the selectMax function. We now move the input sys code and main value code to the outside. When we used it inside the function body, we found that when the function was called, it reported the error. Max value could not be used inside the function body. Why did this happen? Let's find out on the next slide. External variables to the function can only be referenced inside the function but cannot be modified. Reassigning variables inside the function will be seen by the Python interpreter as internal variables are utilized as such. Since the main value variable is defined outside the function, I can only reference it inside the function body. I know that I have defined the variable main value and I can reference it, but I cannot modify the value. I must first assign the value of main value to max value. Max value then becomes a local variable inside the function. Then we can proceed to assign and modify max value, but we still cannot directly modify the external main value. In this case, if we call the selectMax function again, no error will be reported. We've now covered all the content for this lesson. Let's briefly review. We first introduced error types and how to handle exceptions. The error types mainly include compilation errors, runtime errors, and logic errors. Then we talked about how Python handles exceptions in 4 different types of code blocks and how we can customize the process of exception handling. In the second part,
we talked about the problem of character encoding and decoding, the common character sets, as well as garbled character solutions. In the third part, we introduced some rules and patterns of Python function definition, how to set function parameters, as well as lambda functions. Finally, we introduced the concept of variable scope, including local variables and global variables. In this class, we mainly explain some relatively advanced basic knowledge of Python, including error types, exceptions, function definitions, etc. Next, we will explain from the practical level of code. Let's start with the definition of Python functions. Of course, we still use Python's interactive programming environment. Now let's define a function. The function implemented by this function is the function of addition. Review again. In the definition of Python functions, we first use the def keyword as the beginning of the function definition. Next, followed by the name of the addition. For example, we call it addition. The addition is to pass in two values x and y. Then the addition calculation we perform is to add x and y, assign a value to z, and return the result. In this way, we have finished the definition of the function. How do we use this function? For example, let's now let xy equals 1, 2. We can assign values to two variables at the same time in one line, which is assigned in the order of position. 1 is assigned to x, 2 is assigned to y. We can see that x is y and y is 2. Next, we will add the two numbers x and y, that is addition xy. Of course, now x and y are the two actual parameters given a specific value, also called actual parameters. Let's see. What is the result of this function? That's 3. 1 plus 2 is equal to 3. If we want x equals 1, what is y equal to? Y is equal to a string, or is equal to the string a. We do the addition again. Let's see what it will return. Yes, it will have an error. Addition must be based on numeric type. It is not allowed to use a string type. How to avoid this situation will be discussed later. We will continue to talk about Python's error and exception handling. Let's take a few more examples to see the definition of the function. We now define an addition. What if we want to define the function of polynomial computation? Let's look at it again. We define a function of polynomial computation. At this point, we define three parameters, x, y, z. The formula for our polynomial is x plus 2y. As for the spaces between characters, with or without are both okay. This depends on the personal coding style. Double y plus 3 times z. We can write it directly. But often we want to ensure the consistency of this format. Either there is no space or there are all such spaces. We return the result of the calculation so that we define a function of polynomial. In this section, we will explain how to pass in function parameters. We have mentioned before that there are sequential ways to pass in, keywords in, and this hybrid way. Let's look at the way parameters are passed in order. We execute the function. We assign x, y, z equals to 1, 2, 3 respectively. In this way, the incoming parameters are passed in order, and the return value is 14. Let's look at 1 plus 2 multiplied by 2 is 5, plus 3 multiplied by 3 equals 9. So the total sum is 14. If we want to pass in by keyword, we write it like this. Assign x equals 1, y equals 2, z equals 3. It also gets the calculation results of 14, and it is consistent. This way, the parameter is passed in by keyword. We can also mix the parameters passing way, as in order and keyword. However, this hybrid approach requires a constraint. The first parameter passed in must be passed in order. If a parameter passed in by keyword appears, it must be passed in by keyword. We write the correct way first. We write by keyword 1, y equals 2, z equals 3, The first parameter we specify it in order, while the second and third parameters we use keyword, and the return result is 14. Can we mix them in this way? In this case, it will report an error, because for the second position y equals 2, the keyword method is already used. Then the parameter z in the third position must be passed in by keyword as well. Otherwise, a syntax error will be reported. Now we've got a general understanding of the definition of the function, how to call the function and how to transfer its parameters. Let's talk about some common exceptions in Python and how to deal with them. In the previous lesson, we mentioned the error of dividing by 0. For example, assign a equals 10, b equals 0. What is the value of c if c equals a divided by b? We know that the denominator cannot be 0, so when we execute this division, it will report an error of dividing by 0. In fact, during programming, sometimes some exceptions or runtime errors may occur due to carelessness or unclear thinking. Let's take a look at how we deal with it based on the division by 0 error. In the previous theoretical content, we talked about try except, such an exception handling or capture mode. Let's demonstrate how to use the try except module to catch exceptions. For example, what if we try c equals a divided by b? The exception we want to catch is except exception as error. We print this exception, print error. Then look at the error we print, which is division by 0. In this case, at least the program does not terminate. Well, in this case, the program is terminated and exited abnormally. However, in the following way, we capture the exception and print the exception information. According to the printed log information, we can check the logic of the program, rather than directly leading to the termination of the program. Sometimes we may need to take the initiative to judge whether the current situation can continue. If not, we will take the initiative to trigger an exception. We can use the assert statement. Now let me demonstrate how the assert statement triggers or declares an exception. First, define a function called foo and pass in a parameter s. Let's judge whether s is equal to 0. Let's first use the int method to convert s to an integer. We use the assert statement to judge if the value is 0. The exception logic of this statement is, if it satisfies the condition of the following Boolean expression, it will not trigger. If not satisfied, it will trigger. After triggering, it will return a message, which is n is 0. Let's just judge if the value is 0. If it's 0, we will let it go back, and then we construct a division, which is 10 divided by n. If n is 0, the return value is the error message to return naturally. N is 0. If n is not 0, it will get the correct division result. We have defined the function, and we will call it. For example, we passed in s to be 5, which returned 10 divided by 5 to 2. If we pass in a value of 0, the assertion error is triggered, which has the error message n is 0. This error message is defined here, and this is an assertion. Another way is that we actively trigger a new type of error. For example, we define a function my and pass in a parameter level. We judge level. If the level is less than 1, we declare an exception with the noise keyword. The error message returned is the parameter of the invalid level. This newspaper is a grammatical error. This syntax is okay in Python 2, but we did it in the Python 3 series, and there were some mistakes in writing. The correct way of writing should be like this. Raise is an object that constructs an exception. That is it. If we assign level equals 0, we will trigger such an exception. When we call the my method, we will throw an exception. The error information returned by the exception is invalid level. If we don't want the program to terminate because of this exception, we can try except. Try my level, accept exception as error. And print the error information. We can see that the program is running normally. It prints out the error, which is invalid level. Through the raise statement as shown above, we actively dump the exception. This is the end of the coding demonstration. Thank you.